All right, let's start talking about triple integrals in Cartesian coordinates. Okay, let's start with the simplest case here. I imagine that I have a rectangular box with the sides parallel to the coordinate planes here. In fact, in this particular picture I've taken from OpenStax, one corner is actually at the origin. Okay, but that's obviously not always the case. Okay, a triple integral, you can probably guess what we're going to be doing here. We're going to take a box like this and we're going to do what? We're going to partition it up into a bunch of what? Sub-boxes, divided into sub-boxes by planes parallel to the various coordinate planes here. Here you can see we've taken a particular sample. They call this B subscript ijk. Okay? Alrighty. Now, what are we going to do? We're going to do what we always do. We're going to take something like that and we're going to, what? Take a sample point inside each of the boxes here, the sub-boxes that would result. And we're going to do what? Take that sample point and evaluate some function. In this case, that function is going to be a function of all three coordinates, x, y, and z. And then we'll multiply by what? The differential volume here of each little sub-box and add them all up. And then take the norm as the partition, as the norm of the partition goes to 0. Okay, so this is done in this second section here. Okay, so we've got this for each ij, k, and ij and k. We imagine taking what? A sample point like this, x sub ijk star, y sub ijk star, z sub ijk star in each of these sub boxes, b sub ijk. Note that the volume is, well, delta x, delta y, delta z. It may be that these are actually different for different boxes, but that's okay. They've made sort of an equipartition here in OpenStax. What are you going to do? You're going to create a triple Riemann sum. Okay, so we have some supposedly continuous functions of the three variables x, y, and z, and we're going to evaluate that f at each of those sample points, multiply by the differential volume, delta v here, and then we're going to add all those up. Okay, so you notice that triple summation here. Okay, and then what? Like I said, we're going to take the limit as the norm of the partition. That is the length of the largest side of any of the three dimensions goes to 0. And what we end up with as a definition is this triple integral idea. So we would have the triple integral over the box, f of x, y, z, dv. Okay, if that limit exists, and that limit will exist whenever f there is a continuous function of x, y, and z over that rectangular box, meaning its interior. Okay, that's our definition. Now, what we do, we've got a Fubini's theorem for triple integrals. Okay, so this is saying if the function is continuous on that rectangular, I should really say in the rectangular box. Okay, all right, then we can actually what? Compute the triple integral by what? Computing iterated integrals, right? So you could integrate in the x direction first, then the y direction first, then the z direction first. Notice over a rectangular box, the limits of integration would just be constants, wouldn't they? Like I said, this is the simplest case here. Okay, what about this though? Now you considered with double integrals, there was two different ways, even over a rectangle, to write the order of integration, right? There's two different directions because you could integrate with respect to x first, then with respect to y, or vice versa. Now if I'm dealing with three dimensions, I've got dx, dy, dz. How many different ways could I integrate in theory? Okay, I could do it 3 times 2 times 1, 3 factorial is 6 different ways. Okay, so you could integrate with respect to x first, then y, then z, or x first, then z, then y, and so forth, all the way down. You've got 6 different orderings for the way you could actually integrate something like this. But this is the way we're going to do it. We'll actually perform iterated integration here. To evaluate some of these, I'll start with a simple one here. As you imagine here, our region, or I should say our solid of integration, is not going to be so simple as a box usually, okay? So the limits of integration will start becoming variable. Okay? Variable. Let's work an actual numerical simple example here. I'll call that example 1. Okay? I'm going to integrate this. So I'm integrating, let's see, from here, let me just write this larger here. This is very simple here. So example 1. Okay? We'll be integrating from 0 to 7, from 2 to 3. You could imagine the box here over which we are integrating. From 0 to 1, 1 plus x, y, z. Now I'm integrating in this order, dz, dy, and then dx. Okay? How would you perform such an integration? How would you get a numerical answer out of this thing? Well, what you're going to do first is integrate the innermost integral with respect to z. That means you're going to do what? You're going to leave x and y constant. So we could actually write this if you want. Go like this. And then we'll talk about a possible interpretation for this triple integral here, right? What would be the meaning of this thing? Okay, let's do it first though. Okay, so I'm acting like what? X and y are fixed numbers and integrating with respect to z there. So it's like what? We were calling that a partial integration. So I would get what here? When I integrate 1, I would get z. And here I would get 1/2 xy times z squared. Now, where is z going from and to? Z is going from 0 to 1. So let's go ahead and evaluate that. You see at z equals 1, we would get what? 1/2 plus 1/2 xy. When I evaluate at z equals 1, when z is 0, I get what? 0 out of both those terms. So the answer is what? 1 plus 1/2 of xy. Okay, so that's the value of the inner integral, innermost integral if you wish. 0 to 7, 2 to 3. Okay, that inner integral turned out to be 1 plus 1/2 xy. And now we're integrating with respect to y, then x, right? Okay. Now, again, I could do this inner integral. I'm going from 2 to 3. Here, maybe I should come up here and say this is I. Okay, that's I. Now, this is just an inner integral, but this is what? I again. Okay, so I'll make that statement, put a period. Let's work this guy out. 1 plus 1/2 xy dy. So that would be y plus what? 1/4 xy squared. Y is going from 2 to 3. Okay. All right, let's see what we get this time. At 3, we would get 3 plus 3 squared is 9, so 9/4 x, right? Okay, and at 2, we would get 2 plus 2 squared is 4, so it looks like we would just get plain old x there. Okay, now when we take the difference here, 3 minus 2 is 1. 9/4 x minus 1x would be what? 5/4 x. So that's what that inner integral amounts to. This, okay? So finally, to get our answer here, to find what I was, we're going to go like this. Okay? That's the integral from 0 to 7. Okay? 1 plus 5/4 x dx. That looks easy. Okay? Let's go ahead and do that. What would we get? We would get x plus 5/8 x squared. And x is going from 0 to 7. I won't write x equals there. I think we're pretty clear. There's only one variable involved this time. 7 plus 5/8. 7 squared would be what? 49. Okay. Minus 0. And it looks like, let's see, what would we get here? 7 plus 5 times 49. That's 5 times 50 minus 1. So that's 250 minus 5. which would be 245 over 8. 7 times 8 is 56, so we've got 56 plus 245 all over 8. And what does that amount to, folks? Is that 301 divided by 8, I think, if I got my arithmetic correct? Okay. Yeah, I think so. Okay. Alrighty. So there's our final answer for this particular problem. Now, you could change the order of integration. There, like we said, there's 6 different ways of actually integrating this, right? You will get the same answer every single time. Obviously, I don't want to do it all these other different ways here. Okay? Integrating over a rectangle is pretty easy because you don't have to worry about the order of integration. Okay? Right, sometimes it might be a little bit easier in one direction or the other, but that would simply be, in a case like that, that would occur only in cases where, the integrand is some special form or something. That would be because of the integrand, not because of the shape of the box. Now, for a quick interpretation of what this might mean, and in fact what I actually had in mind here, well, I think we can all see this box in our minds, right? Z goes from 0 to 1, Y goes from 2 to 3, X goes from 0 to 7, so you could have that box in your mind. We could have graphed that, but that's easy to imagine here. What might this little thing be here, that integrand? In this particular case, I'll call it f of x, y, z. Okay? What might be an interpretation of this? Well, what I actually had in mind is this is maybe a density function. And I'll work some more problems along these lines. A density function. So if my integrand had only been 1 there, okay, this problem, okay, instead of f of x, y, z, that whole thing had just been 1, all I would have been doing when I integrated was finding the volume of the box, which would be awfully easy to do. You wouldn't even need calculus for that, though. So if the integrand was 1, then you'd just be finding the volume of the box. But with this function in here, if that's a density function, okay, which varies from point to point within that box, what you've actually calculated here is the total mass of the box, okay, the total mass of a box. So we've never considered a question like that before in calculus, where you have a density function that changes over 3 space, right? Okay, we couldn't do those before because we didn't have the idea of triple integrals, all right? Okay, we'll continue with some other examples here in just a second. Okay, and the problems we'll be looking at, most of our figures will end up being z-simple or a sum of z-simple regions. Let me explain what I mean here. Okay, I mean it z-simple in the following sense. If I'm attempting to integrate over a solid D some function f of x, y, z dv, what I'm going to imagine my z-simple situation is this. I'm actually integrating over a region R of the xy plane together with what? The region is such that over that region R of the xy plane, z is bounded between 2 functions of x and y. I call this one the lower function of x and y and the upper function of x and y. So that when we use Fubini's theorem and as an iterated integral, the first thing we will do is integrate with respect to z going from L to U of f of x, y, z. And then once we get that result, which will be in general what a function of both x and y, then we'll integrate that resulting function of x and y over the region R with respect to dx, dy, or dy, dx, depending on the order that appears to be easier. Okay? And now if it isn't z-simple, then I'll break it. The problems I'm going to take, you're going to be able to break it into a sum of z-simple solids. Okay? So let's go ahead and take an example where I actually have to break this into a sum of z-simple solids. Okay, let's see if you can see this. The density of a solid is given by this. So my density function is f of x, y, z is 16z grams per, say, cubic centimeter. Now all my length measurements will be in cubic centimeters. and I ask you to find the mass of the solid in grams. Now, here's the solid that we're talking about here. Okay, so it's a sort of a triangular prism-looking thing here, somewhat pyramid. Okay, but this is the idea. Okay, I've got one plane, which is this. Z equals 1 minus 1/2 x over here. And I've got another plane, which is what? Z equals 1 minus 1/4 y. Okay? And these intersect, and you guys can see, all the other boundaries of this solid are the coordinate planes. So the xy plane, the xz plane, and the yz plane, as you can see there. Okay? So all the boundaries of this figure are planes. Okay? Now, let's go ahead and see here that this figure is not z simple, but it can be broken into a sum of two z simple regions. Okay, now these two planes here that we're looking at, z equals 1 minus 1/2 x and z equals 1 minus 1/4 y, they actually intersected a line here in 3 space, as you can see. Okay, if I imagine projecting that line from 3 space down into the xy plane, then you see what I'm going to actually be doing is integrating the solid over region R1 here of the xy plane and R2 over the xy plane. So I'm going to be breaking it up into two z-simple solids this way, okay? All right, so imagine a cut being a vertical plane running through this dashed line in the xy plane, cutting through this solid. That would break it into two z-simple solids, okay? Now, while we're at it here, we need to start. Can you find the equation of this dashed line here? Okay, I'm going to need to establish that when I'm integrating over R1 and R2, okay? Let's see, the equation of the dashed line here would actually be, well, if you look at it in the xy plane here, we've got one point at the origin, okay? So forget 3 dimensions just for a minute here. Okay, I'm just talking about the region R1 and R2 of the xy plane here. Okay, and this point has coordinates what? 2, 4. Well, the equation of the line between 0, 0 and 2, 4 would be what? You can see that pretty simply, that y would be 2 times x. Okay, so we need to keep that in mind here. I'm going to put that down right there. That's that dashed line there. Okay, that's the dashed line. Okay, now, if I say this whole thing is D, the whole solid, I'm performing the triple integration over that solid D, okay, of my function f of x, y, z, which turns out to be just what? dz. Now I'm going to imagine integrating in the z direction, and then the x direction, then the y direction, or maybe the y direction, then the x direction, but certainly in the z direction first. But for now, I'm just going to go ahead and write what? dv, okay? Okay, differential change in volume here. All right, now keep that in mind. All right, now I'm going to break this into the sum of 2 iterated integrals, okay? Now I'm going to write it like I was showing you there with the z-simple situation here, where I'm going to be integrating over an R1 and an R2, and then I have a situation like this, a lower function of x and y and an upper function of x and y that I would actually calculate first. Okay, well, we're refraining from calculations for the moment though, right? All right, I'm just going to integrate over R1, so don't try to do too much at once. Okay, the inner integral, where would, so over R1 here, okay, where would z be going from and to? Okay, so this R1, maybe I'll use parentheses here, because you guys now understand the R1 refers to the x and y here. Anyway, where is z going from and to? Z's going from the xy plane, so that just has equation z equals 0, up to what? This plane right here. Well, what's the equation of that plane? It's z equals 1 minus 1/2 x. Okay, and now my density function there is 16z, so I put that in. Then I'm integrating with respect to z. And then I'm just going to write here dA. Okay, I haven't decided which direction to do what. Integrate with respect to x or y first, so I'll just say dA. So that stands for what? Either dx, dy, or dy dx. I'll decide later. Now, I need to add to that. I'm not done yet, right? I've got to integrate over R2. Okay. Where's z going from and to? Well, once again, z is going from 0, the xy plane, out to this plane, which is what? Z equals 1 minus 1/4, 1/4 y, and then our density function 16z, so we're going dz, and then we'll go dA again, deciding the order of integration there again. Okay, so this is it. Don't try to do too much at once. Now we're going to have to evaluate each of these independently. Okay, each of these independently. So I've got two integrals to figure out. Now we need to get the order of integration right, everything like that. Okay, so let's go ahead and let's look at this first integral here. I'm actually not that interested in the answer. I'm mostly interested in that you folks are able to set up the integral properly, right? Because what? If you can't set the integral up properly, then there's really no point in continuing here. Okay? All right, let's look at this first integral where I was integrating over R1. Okay? Integrating over R1 here. R1, I think I will integrate in the following way. I'll integrate with respect to y first and then with respect to x at the end. So I'm going to do this. Here comes my triple integral. Now this first part is just a copying exercise. Z goes from 0 to 1 minus 1/2 x. Okay, this was 16z dz. Okay, then I said the y direction, then the x direction. Okay, now where is y going from and to in R1? Well, R1 is a triangle, right? It has a boundary being what? The x-axis. The upper boundary for y is this line, right? So in terms of x, that would be what? Going from y equals 0 to y equals 2x. Now, where is x going from and to here? It's going from 0 to 2. Okay, so that's my first integral. Okay, maybe I'll give that a name. I'll call it I1. Okay, it might be convenient later. So the first integral. Now, this isn't such a tough evaluation, right? That doesn't look so bad. Okay, that doesn't look bad. Let's talk about I2, the other integral. Okay, so let's go ahead and do this. All right, in the second integral, we've still got that same integrand, so that's 16z. And let's see, we were going from 0 to 1 minus 1/4 y. Okay, and now I'm integrating over R2 there. Okay, R2. Well, how do you want to do that? Okay, how do you want to do that? Do you want to integrate in the x direction first, then the y, or the y, then the x direction? Okay, there's different ways you could approach that problem. You could do whatever you want. Okay, you could do whatever you want. I'm thinking about just sticking to the same order here, but as an exercise, you might, turn it around. That's always good practice. Make sure you get the right answer, though it ends up being a lot of work here. So I'm going to go dy dx again. Now you got to be careful here. Where is y going to be going from and to? Y is going to be going from the dashed line to x, right? Y is going to have to be a function of x for this to make any sense. Up to what? It's always going up to and stopping at 4. Now projecting R2 down onto the x-axis, you see x is going from 0 to 2. Notice because of the difference in these two, the second integrals, that adding these isn't just a mechanical operation. And, same thing here, of course, with these inner integrals. But there it is. So our integral, our answer is what? Going to be obtained by adding these two individual integrals. Okay? So let's go ahead and work these on separate paper here. Now let's go ahead and work out these integrals to get a numerical answer here. Okay, Let's do this inner integral first. So I'm starting with I1 here. The integral from 0 to 1 half x, 1 minus a half x I should say, 16z dz. Antiderivative you see from the power rule would be what? 8 z squared. Okay. Going from 0 to 1 minus 1 half x. So that would be 8 times 1 minus a half x squared minus 8 times 0 squared. And you could see that that would be what? 8 times 1 minus 2 times the product of the two would give x, right? Plus 1/4 x squared. This is 0 there, so let's multiply through with the 8. 8 minus 8x plus 8 over 4 is 2, so it's 2x squared. Okay, so that's the value of the inner integral. Okay, then we're going to integrate that result with respect to y. Notice that this did not involve y at all, so this would be easy to integrate with respect to y. So it's acting like what? This is acting like a constant. So we've got 8 minus 8x plus 2y squared. The integral of dy is y. Y goes from 2x to 0, so it would be this polynomial times the 2x minus 0, which is 2x. So that's what? 16x minus 16x squared plus 4x cubed. Okay, so that's the result of the second integral here. And then finally, to get I here, I'll finally make a statement about I sub 2, or I sub 1. Integral from 0 to 2, 16x minus 16x squared plus 4x cubed dx. Okay, fortunately the integrations are easy. 8x squared minus 16/3 x cubed, even if the numbers are not pretty here. At least we're only integrating polynomials, eh? Okay. Okay, did I get it right? Does it look good? Okay, I think I'm okay here. All right, let's go ahead and work the numbers here. 2 squared is 4 times 8 is 32. 8 times 16 is what? 128 over 3. 2 to the 4th is 16. And you can see I'm subtracting 0. So we would end up getting 48 times 3 minus 128 all over 3, right? So it looks like I1 is equal to, I'll box this in. Let's see, what's 3 times 48 minus 128? Let's see, that would be 130. Let's see, 3 times 8 is 24. That's 144, isn't it? Minus 128 over 3 is that 16? 16/3. Okay. I'll box in that answer, even though that isn't my final answer for the whole problem, but there's I1. Okay. What about I2? Okay, we have to start over again with a second integral. Let's go ahead and work this one. Okay. No reason to wait here. 16z dz. Once again, that's 8z squared. Z goes from 0 to 1 minus a quarter y, so very similar to the previous. That's 1 minus a quarter y squared minus 8 times 0 squared. So that's 8 times 1 minus a half y plus 1/16 y squared, right? Okay, so that'd be 8 minus 4y plus 1/2 y squared. So that's that inner integral. And then we need to integrate that from what? Y goes from 2x to 4. So this would be 8 minus 4y plus 1/2 y squared dy, which would be 8y minus 2y squared plus 1/6 y cubed, going from 2x to 4. 4 times 8 is 32. 4 squared is 16, so that gives me 32 again. That's nice. 4 squared is 64, so that's 64 over 6, which is really 32 over 3, isn't it? Okay, and then I'm subtracting 16x to, I guess that's 8, isn't it? X squared. Okay, 4x squared, negative 2, negative 8x squared. Okay, 8, 6, so what is that, 4/3 x cubed? Okay, what are we getting here? What does this amount to? We've got 32/3 minus 16x plus 8x squared minus 4/3 x cubed. Okay, modulo any errors I might have made. Okay, so I subscript 2, integral from 0 to 2, 32/3 minus 16x plus 8x squared minus 4/3 x cubed dx. That would be what? 32/3 x minus 8x squared plus 8/3 x cubed minus 1/3 x to the 4th, going from 0 to 2. This at 0 is 0, so I'll just stick this in here. 64/3 minus 32 plus 64/3 minus 16/3. Okay, so this would be 128, right? 128 minus 16, wouldn't that be 112/3 minus 32? Okay, so that would be 32. That would be 112 minus 96/3, and that's 16/3 also. Is that right? Yeah, I think that's correct. So I sub 2 is 16/3. So that means the value of my whole original integral was 16/3 plus 16/3. So the value to the whole problem, which I'll call I, is 32/3, I think. Okay, at least that's what I got. Alrighty, well, there it is.